Now we can use the definition of the velocity or the instantaneous velocity. We have that the limit of delta t n approaching 0 of the Vx n average is equal to the velocity Vx n. Okay, this is, we have discussed this before. This is the definition of the instantaneous velocity or just velocity. Okay, so we can rewrite the above equation as the delta x is equal to the limit of delta Tn approaching 0 of the summation of the Vxn. Now we just write the Vxn because it's not the average but it's the instantaneous velocity time delta Tn. Okay, this kind of equation is a summation of the last pieces of number with each has small value. Okay, now delta Tn can be very small because we take the limit here. So this piece of number is very small, but the number of n can be very large now. So this is a summation of the large pieces of number, and each number is very small. In calculus, we have a technique to calculate this kind of summation. We use the concept of the integral. We use the concept of the integral. That is, we can write delta x is equal to the integral of ti to tf of Vx dt. Okay, it's ti to tf integral of Vx dt from ti to tf. This is the definition of the integral. So from this relation you can see that the integral is nothing but just the summation the integral is just a summation, and we will use this meaning of the integral again and again in our study of physics. This is the meaning that we always use in our calculation, so please try to understand this. However, from the calculus we know that the integral from ti to tf of Vx dt is equal to the area under the graph Vxt, right, over the interval xi to xf. Okay, it means that if you have the graph of vxt, vx and t between this interval ti and tf, we know that the area under the graph is equal to this integral. Okay, so we have that the area under the area under the vxt graph is the displacement. Okay, the area under the VT graph is the displacement f minus xi. So this proves the assumption we used in the previous section. Okay, we assume that from the result of the constant acceleration motion, but now we prove that this is true in general. Okay, so if we look at the VT diagram for an object moving with a constant velocity, we will have this kind of graph, and the area under the graph here is equal to the displacement over the time ti to tf. This area is equal to Vx tf minus ti. Okay, and from our calculation, this is equal to the xf minus xi, and we have the kinematic equation for constant velocity back again. Okay, now using the similar idea, we can rederive the kinematic equation, but now we will use the calculation to achieve that as follows. Let's start with the acceleration. Okay, assume that we know the acceleration as a function of time. We know the acceleration as a function of time, so it means that we know the ax. Okay, let's specify this axt graph. Okay, because we know the functional form of axt, so we know in principle we know the axt graph, and from the concept that we have just discussed, we know that the area under the axt graph under the axt graph is the change of the velocity. So it's equal to Vxf minus Vxi. But we know that the area is the integral. So we have that Vxf minus Vxi is equal to the integral of Ti to Tf of Ax dt. Okay. This is a general relation. We can calculate the change of the velocity if we know the acceleration as a function of time. Okay. Now, for the simple case, we have studied in this chapter that if we have that Ax is a constant, so when we do the integral of Ti to Tf of Ax dt, but Ax is a constant, so we can take Ax out of the integral process. So we have that it is the Ax of integral of Ti to Tf dt. And from the calculus, if you go to the math textbook, we have that this integral from Ti to Tf dt is just equal to the Tf minus Ti. Okay, so we multiply it by the Ax. So we have the area under the curve, and this must equal to the Vxf minus Vxi. Okay, so we have the kinematic equation of the velocity for the object moving with a constant acceleration back. We can expect this from our previous discussion.